Hello everyone and welcome to Big Data Processing in Python. I am Arsal Andeshkam, your data science lecturer. With the advent of big data in every field, you may need to analyze increasingly large data sets. In this course, I'll teach you some of the tools and techniques for processing data that may be too large for your computer. The approaches I'll show you are scalable in the sense that they are easily parallelized and work on discrete blocks of data. Scalable code lets you make better use of available computing resources and allows you to use more resources as they become available. When we create a vector, data frame, list or environment in Python, it is stored in the computer memory RAM. RAM stands for Random Access Memory. It is where Python keeps the variables it creates. Modern personal computers usually have between 8 and 32 gigabytes of RAM. Datasets, however, can be much bigger than this stuff. For example, when we want to run a machine learning model, we may process hundreds of gigabytes of data. In this course, we won't process datasets that big, but we will see some of the tools we use to create tasks that can be run on datasets that may be too big for our computer's memory, but less than the amount of hard drive space we have available. When a computer runs out of RAM, data that is not being processed is moved to the disk until it is needed again. This process is called swapping. If there is not enough space to swap, the computer may simply crash. Since the disk is much slower than RAM, this can cause the execution time, which is the time needed to perform an operation, to be much longer than expected. The scalable solutions we learn here move subsets of data into RAM, process them, and then discard them, keeping the result or writing it to the disk. This is often orders of magnitude faster than letting the computer do it. And it can be used in conjunction with parallel processing or even distributed processing for faster execution times for larger data. So why is my code slow? If we are processing all elements of two datasets and one data is bigger, then the bigger dataset will take longer to process. However, it is important to realize that how much longer it takes is not always directly proportional to how much bigger it is. That is, if you have two datasets and one is 2 times the size of the other, it is not guaranteed that the larger one will take twice as long to process. It could take 1.5 times longer or even 4 times longer. It depends on the complexity of our calculations and which operations are used to process the dataset. Let's change the panel to the VS Code and see our code intended to compare the time complexity of sorting of an input data of varying size. While I let the code to be running, I explain the main part of the code. We import necessary libraries, or we then create a list of integers representing different vector sizes to be used for benchmarking performance. And in our benchmarking loop, we first generate 5 random vectors and then measure how long it takes to sort each of these vectors. And finally, we convert our results to data frames for visualizations purposes. So let's have a look on the result, and it is a box plot which shows sorting times for varying vector sizes up to 10 million integer elements. X-axis is labeled with vector size and represents number of elements to sort from 100K to 10 million. Y-axis represents time taken in seconds to sort and measured across repetitions per size. Key observations are, for sizes from 100K to 1 million, sort time increases gradually, then jumps dramatically at 10 million elements. This means that we are hitting RAM limitations and consequently more page swaps, and more CPU time due to analog and complexity and growth of sorting algorithm. Hence, NumPy's sort remains efficient and stable up to 1 million elements. Beyond that, performance degradation becomes significant. Hence, for very large data, we need to consider optimizations like out-of-core sorting. Let's see how Dask package helps in big data processing. Dask is a parallel computing package based on Python. I have imported Dask data frame as DD. Then the array, the vector of various sizes, becomes a data frame, which is a one column table. And the large data frame is then splitted into chunks that Dask can process separately. And Dask sorts the data by sorting each partition individually, then combining them into a full sorted result using an external on-disk merge. Let's go back to the presentation deck and compare the results of these two versions of implementations. The top left shows how fast NumPy can sort. Even for 10 million numbers, it finishes in under 0.4 seconds. And the bottom left chart shows the cost. Memory use goes close to 250 megabytes because NumPy needs extra space while sorting. Now compare these to Dask in the right. It also finishes but takes about 3 seconds, much slower. And in the bottom right, we see memory usage climbing even higher, over 800 megabytes. That's because Dask first turns the data into a pandas table and splits and shuffles it. Therefore, use NumPy if your data fits in memory. It's fast and light. But for really large data, Dask is better. Just make sure to use it in the right way, with chunks and arrays, not full tables. Let's talk more about it. Dask is a Python library that makes it easier to work with big data or speed up computations even on a laptop. Here are the main benefits in simple terms. First, if we already know how to use pandas or NumPy, Dask feels very similar. We can write almost the same code. Second, imagine we have a table with 50 million rows, but our computer can only hold 5 million rows in memory at once. Pandas would crash or slow to a crawl because it tries to load the entire table at once. Dask automatically breaks the table into chunks, works on each chunk separately, and only keeps a little bit of data in memory at any time. It also writes the intermediate results to temporary files instead of crashing. These allow processing datasets much larger than RAM. Dask is great at parallelization. On a normal laptop, Python code often runs on just one CPU core at a time. Dask can split or across multiple cores, so operations like sort a large table can run faster using all CPU cores in parallel. Fourth, scale up is now easy with Dask. If our problem grows from, say, 10 gigabytes of data to 1 terabyte, we can point Dask at a small cluster of machines instead of just our laptop. Dask will distribute those same chunk-based operations across many servers. This scalability is mostly transparent. The same code that ran on our laptop can often or on a cluster without huge rewrites. And finally, Dask is lazy but smart. When you call a Dask operation like sorting, Dask doesn't do the work immediately. Instead, it builds a task graph that is a to-do list of all the steps needed. Only when we explicitly ask for a result, Dask actually runs each step in the most efficient order. This prevents unneeded work and helps Dask optimize the whole workflow end to end. Okay, in case you slept through the class, and I'm sure you didn't, here are your takeaways. Run is precious. Swapping hurts performance. Big data jobs slow down or crash when everything is loaded at once. Move subsets into memory, process, then discard or persist the disk. Dask with its precious characteristics such as automatic parallelism and out-of-core chunks brings a much bigger pandas or NumPy. And finally, choose the right tool for the job. If your data is small or medium, stick with fast, simple NumPy or pandas. And if you are with bigger than RAM data, switch to Dask arrays or data frames. So the key message is understand your data size, monitor memory, and pick the workflow that keeps computations fast, reliable, and ready to scale. Now, it is your turn to come with your next week assignment, delivering a scalable, not loading all data frames into the memory and is faster than NumPy. Keep calm and let Dask do the heavy lifting. Until next session, happy Dask streaming!